All right, we're going to continue on with a couple more codings, coding of certain things before we go into Prim's minimum spanning tree, which is what you'll be doing for the lab. Well, let's talk about a couple of things, and then y'all probably want me to do breadth first traversal instead of depth first, I'm going to assume, which is fine. It's great. But clear edges, we already did that. If you wanted to add a vertex, what would you do?
All you'd have to do is add another list, right?
Yeah, if we're over here, camera got moved just a little. We wanted to add one vertex over here. What would we do?
Just add another.
Yeah, you'd increase your vector by 1, and then you're done. Yay! If you wanted to add 2 of them, and you're like this, what do? Right. Isn't that great the STL does all that for you? And then it'll do that. What if you wanted to delete 3?
Take it out. STL. Fix it right there for you. Yeah.
You're going to first want to move everything up.
Yeah.
Make sure you start at the 4 first, move it up, and then when you're done, decrease the size, or cut the size off by 1, which is actually still a lot easier than the matrix. All right, print. Okay, traversal. I will code one of these up for you. Do you want me to do the depth one or the breadth one? I showed you the breadth one last time with the matrix, so I'm leaving it up to you. I know breadth can seem like a very hard way of going about it. By the way, in general, the breadth first traversal is more efficient than the depth first in general. Malik, right? Yeah, we experienced that in a competition.
I'd say depth.
You want to do a depth this time?
Yeah, we did breadth last time.
I mean, I was thinking that would be the best way to do it. Then you can see how each one is done. All right.
You can change your depth first.
What's that?
I say it should have done breadth first.
Well, you're going to find that breadth first, you take the other code and you kind of just change it to work, and it'll.
That's what I was thinking you probably do.
Yeah, it's actually going to be fairly nice. Let's go ahead and do the breadth or the depth first one.
So like, is this all like the same lab, or are we just gonna start using lists instead?
It's, yeah, you're going to redo your graph with the adjacency list, and then you're going to do Prim's minimum spanning tree instead of Dijkstra's shortest path. It's going to be the next lab. That's it. Okay, so we're going to do this recursively. Actually, we can do it recursively right off the bat, which is great. Well, no, not quite. Not quite. Because at depth first, what do we need to keep track of?
Where you are.
Where you are. That's the node that you're, oh, yeah, where you are. So we have to keep track of where you are. So we're going to have to create a separate recursive algorithm for this. Let's go ahead and start that. So we have the function we want to call. We want to win the node. Ooh. Yeah, the node we're currently visiting. Anything else? Ooh. So we probably want to. Usually with recursive calls, your main call just calls the setup for the next one. So we'll do depth first traversal, passing in visit, and we'll probably want to start at 0. All right. Anything else we need? So that's where we are. How do we know when to stop the recursion? Remember, you're doing a recursive call. First thing you do, when do you stop?
It's null. Node is null.
Are we ever going to call when the node is null in a JC list? No, because we just have a list. Let's go take an example. Maybe I can help you out. Let's go, let's pretend that there's one right here. Arrow. we start at 0, great. We go to 3, okay. We go to 5, okay. We go back to 0. Wait, should we go back to 0? No. So what do we need to keep track of? Because if we could, then we'd just be doing this the whole time.
Like the parent node?
The parent node. Well, the parent of 5 is 3. So we
Need to keep track of the original.
need to keep track of the original
Start?
Well, that was just 0. What if there was, you go to 4 and then 4 could go all the way to 3?
So you need to keep track of everything you visit.
Right. We need to keep track of everything we visited.
So an array.
We could use an array, but what does that really sound like? Think STL.
A set?
A set. We're really keeping track of the set of numbers that we've already visited. So we can just use a set. So we can do, let's see, what's it called? STD of a set of, and we don't care about the weights. We only care about what nodes we visited. So we're going to just make it a set of ints, and we'll just call it visited. Now we're going to have to go ahead and include this up here, but that's perfectly fine. Oops.
Wait, sets already in there.
Oh, right, we're doing great. All right, and then we're going to want to call that or send that to our function call. So we're going to need to also add that. Let's go ahead and make this a new line, otherwise it's going to get pretty ugly. Set of int, and we're going to do it by reference so it doesn't create it every time. Okay, so we're passing in the function we need to call on the node that the visiting, and a list of visited, or a set of visited nodes. All right. So during recursion, what's the first thing you do in recursion?
Your break statement, right?
The base case, right? Base case, your break statement. When do we get out?
When all the nodes have been visited.
Base case, nodes, all nodes have been visited.
No, I guess when you're,
So let's go back to this, to the picture. And let's pretend we have this right here. 0 needs to go to 3. That's fine, right? 3 going to 5. That's still okay, right? 0 going to 5, is that okay? No. No. How would we know not to go to 5 anymore? Not to go to 0, sorry, thank you.
have to mark 0 as visited.
It visited. So what's the base case then?
But basically, if 0 is visited.
Right, if 0 has been visited, don't do it. Right, so first we stated in English, if not 0, but in this case, node, if node has been visited, escape, or return. All right, now how do we check that? Well, visited dot, let's pull up the good old STL of set. I thought it was going to come up real fast, then I realized that was Google coming up real fast, not the reference. All right, what do we have? Well, we have clear find. That looks good. Wait for it. Find, passing in the value, which is an integer. It returns an iterator. So let's look at some example code. Let's see. Go iterator, find. Doesn't actually tell you. But let's see. 2 elements, val, return values, an iterator to the element val if find or set : int otherwise. So, in other words, this is a little confusing because of how the STL does it. But it's going to return an iterator. If that iterator is equal to end, then it did not find it. If it's not equal to end, then it did find it, and the iterator is actually representing where that value is in the set. So if we want to just test real quick if it's part of the set, dot find of node does not equal, and then we got to do this, set sub, oops, std, set sub int, end. Well, let me make sure I did that right. Oh no, I did that wrong. Visited.end. We return. Because it found it. Let's at least start setting up the test cases for this. Let me go look, do a quick ls on our tests. We have breadth. All right, we're going to go ahead and copy breadth over to depth test. CPP. And let's go over here and let's open it up real fast. We need to do AL. L right there, add a bunch of eds, print it, and then we'll do depth. Oh, I shouldn't have done that. Depth first traversal. Passing in print. We'll go ahead and make depth test. Did not like that. Oh, I know why. Because we never actually declared this function in the header file. So I'm going to go ahead and declare it real quick. We'll go ahead and make it private. Shouldn't be any problem with that. All right, everyone's seeing what I'm doing so far? Sometimes I go into auto mode. All right, good. Hey, look at that. All right, so it gave me the graph, but it didn't do anything afterwards. It did call our function, but it didn't. The function did not actually do anything. Calls it, but didn't print anything out, which is actually just fine. All right, so we're going to close that. All right, so now we know that node has not been visited. So what do we do second?
Now we gotta go to the next one.
All right, we want to go to its children, but before we go to its children, this is a depth first traversal. So once we get to the node, we need to mark it as visited and actually visit it as well. So we're going to visit the node and then 3 mark as visited. So to visit the node, we have the function called visit, so we'll just call it passing a node. Mark it as visit. Let's go look at the STL real fast. And looks like it's insert. So we'll just do visited.insert node. So now it's been marked as visited. Let's go ahead and run the code real quick. What should it do with just this? It'll probably just print off 0. Right. All right, good so far. Now what do we do next?
Now you gotta go to the children.
Go to each. You're right. Just say it again. I didn't quite hear.
So go to the children
Go to each children and do what?
and mark them as visited.
We don't actually mark them as visited. What are we going to?
Oh, and then we go to theirs.
All right, we'll first go to the children. I'll let y'all think about this. Go to each child. So, well, we've already written the for loop, so let's copy and paste that. All right, and it's mgraph sub node, yeah, which is the only thing it could be. The only thing we have at this point. All right, we're going to go to each child. It represents a pointer to the child. And then what do we do?
Do the recursive call.
There we go. We do the recursive call. Still passing in visit. What's our new node? No, it's not node because that's where we are. IT, but IT is a pair of ints and W, so it's IT of first. And then what else do we need to pass to this? Visited. Are we done? We're close. Maybe. All right. 0, 3, 4. So it did actually recurse. Look at this graph real quick. What's the problem? How do we get to 1? You don't. Right. So, right. So this was I was talking about where you, in your code, since you're doing a traversal, with the breadth first, you found the next node that hadn't been visited, and then you called depth first traversal on that. We're going to do the same thing here. And I'm going to go ahead and code this up real quick, because the solution is easy, but it's hard to, for some reason, it's a little tricky to keep in mind what's going on. That's how many nodes there are. And if it's this check right here. If it hasn't been visited, then we're going to go ahead and call the recursive depth first call. Obviously, when I is 0, it hasn't been visited, so it's going to call 0 first. And then it's just going to go through each graph and find something that hasn't been visited, and then only call that function if it has not been. Everyone see what I'm doing here? You okay with that, Malik?
Yeah.
All right. How you doing, PJ?
All right.
All right. It goes 0. Whoops. Oh, this check is backwards. If it did not find it, do the depth first search. That's what I meant to do. 0, ooh, didn't work out that time. Is visited? How did that get wrong? Size I++. Ooh, something's not right here. 0, 3, 4, and then it should have called that next. Well, let's see what the problem is. That didn't make any sense. So if visited equals the end, oh, haha, is it 0?
Aye.
Aye. 0, 3, 4, 1, 2. Boom. All right. How are we doing? So what do y'all think so far of the Adjacency list versus matrix?
Pretty cool.
It's actually easier with the STL, but if you didn't have the STL, it was going to be a lot more coding. Because you'd have to create your own linked list, your own vectors, et cetera, et cetera. Yeah, yeah. So the STL is what, sorry?
I said that gives me chest pains.
I think the first time I taught this course, I made them write it out without the STL. Yeah, and then we didn't do it again after that. I mean, for me, it's like, yeah, we'll just keep writing for loops, we're good. But yeah, they didn't like that afterwards. But y'all know, the important part is you understand what the STL is doing for you. And that's really what's important in this class. All right, we're going to stop here. We're going to talk about Prim's minimum spanning tree. And then I'm going to go into your lab, and then we're going to talk about the course from there.